Right, here we go. So now we get to learn about sort of how forces affect the motion. All right, so we're going to learn what is called Newton's first law. It is often called, I just realized I didn't print this anywhere, the law of inertia. All right, so if you ever hear somebody refer to the law of inertia, that is another name for Newton's first law. All right, and I'm guessing that you already know this. You probably learned this in middle school. Oh, I did say it. Oh, there. Okay. All right, so we know what a force is. Newton's law tells us how forces affect the motion of an object. All right, so obviously we'll start with the first one. All right, so Newton's first law says an object at rest will stay at rest, and an object in motion will stay in motion unless acted on by a net force. Okay? A lot of times teachers say an object will stay at rest, object at rest will stay at rest, object in motion will stay in motion unless acted on by an outside force. And I don't love that because it makes it sound like every outside force will change the motion of an object, and that's not the case. As I showed you in the last video, here's an outside force on my desk, but it's still not moving, right? Because the idea here is my force isn't enough to overcome static friction. Sorry, you don't know what static friction is yet. It's not enough to overcome friction, and so the desk doesn't slide. So even though there's an outside force, there is still no net force, right? And so as a result, the object at rest stayed at rest. Okay? So an object at rest will stay at rest, and an object in motion will stay in motion unless acted on by a net force. So that's the way that, it should sort of be stated in words. But what I find is students have a tough time applying this concept to problem solving, right? Like if I give you a problem and say, Roy's pushing this box and what's going to happen? Just knowing this doesn't necessarily help. So here's how I like to write it. And I know this sounds really like ego-y because I named it after me, but I don't know, whatever, it is what it is. You guys know me well enough to know that, yeah. Okay, so here we go. So here's my law, my sort of version of Newton's first law of inertia. All right, so here's what Newton's first law says. It tells us that if the net force on an object is 0, then that means the acceleration is going to be 0, okay? If the net force is 0, the acceleration is 0. And if your acceleration is 0, remember what that means is that your velocity is constant. It doesn't necessarily have to be 0, but it's constant, all right? This is super important, okay? Net force being 0 means acceleration is 0, which means the velocity is constant. It could be moving as long as it's moving at a constant velocity, all right? So here's how I write it in shorthand. Newton's first law says this: either all three of these statements are true or all three of these statements are false. So if your net force is 0, that means your acceleration is 0 and your velocity is constant. Or conversely, if your net force is not 0, then your acceleration is not 0, and that would mean your velocity is changing, right? That's what Newton's first law says. All right? So what this is telling us is that in general, you have to have a force, a net force, I guess I should have said, a net force to change the velocity of an object. You need a net force to get an object moving or to cause it to speed up, but not to keep it moving. Okay, you need a net force to stop an object or cause it to slow down, but not to keep it moving. And this will be a couple chapters down the road, but while we're at it, it also means that you need a net force to make an object turn, but not to keep it going in a straight line. Okay? So please, this is huge, please don't make the mistake of thinking that because an object is moving, there has to be a force on it. That is not the case. You can have an object moving with no forces on it. All right, you need a force to get it moving, but once it's moving, you don't need a net force to keep it moving. All right, so here's our example. All right, and so I'm going to edit in a little video of me pushing a cart. All right, so here's what the scenario is going to be. It says, imagine a person trying to push a heavy cart across the room. All right, so to keep things simple, we're going to kind of pretend there's no friction between the floor and the cart, and I imagine I'll probably, as I go through this, talk about what if there was friction, right? So I'm going to pause right now, and we're going to edit in a video of me, pushing a cart. Okay, so you can see I'm about to push this, right? So right now there are really no forces acting on the cart, right? Nothing's pushing it forwards or backwards. So our net force is 0. That means the cart is not accelerating. Its velocity is not changing. It is just staying at rest. All right? Now in a minute here, I'm going to push the cart, and what you'll see is the velocity of the cart increases. okay? And it happens gradually because the cart is pretty heavy, okay? So here we go. So here's me pushing the cart. So while I'm pushing it, oh, there we go. The velocity increases. Velocity increases. Then at the end, you'll notice I let go of the cart. But the cart kept moving, right? Because now there are no forces acting on it, right? The wheels are there to kind of simulate the ground being frictionless. Now, technically speaking, there's going to be some friction there. So the cart does slow down a little bit. But essentially, from the time I let go of it until it hits the table at the end, the velocity is constant. All right, let's watch that again. Pushing, now the velocity stays constant, boom, until that external force from the table stops it. Okay, let's watch it again. Velocity 0, velocity is increasing while I push it, velocity stays constant, velocity decreases, right? Okay, there we go. So that was me pushing a cart across the floor yesterday. Ooh, editing. This is a new capability, so I'm excited about the editing. All right, so let's see. So what happened? So at the very beginning of the video, the cart was just sitting there, right? So here's the floor with the cart, and it was just sitting there, right? Technically, we've got gravity and normal force. Again, we're not going to worry about that for a couple days, all right? But that was it, right? It was just sitting there. So the idea is the net force here was 0. That meant, right? Because I was just standing over here, right? And this was, so this is me, right? Not pushing it, right? And so since there's no net force, that means the acceleration is 0, and so our velocity is constant. And in this case, it happens to be a velocity of 0. All right? So that was sort of the first part of the video, right? Then I started pushing it, right? So force of Hecker, right? So I pushed it with some amount of force. Whatever, let's pick a number, maybe whatever, 30 newtons, doesn't matter. All right? And since I was the, other than gravity and normal force, I was essentially the only force on it, right? Oh, well, that means my net force is 30 newtons, which notice that's not 0. Oh, that means that we had an acceleration that's not 0 in the same direction as that net force. Okay, and as a result, the velocity increased, right? And the velocity of the cart went faster, 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 as long as I pushed it, okay? And then I let go of it, right? I stopped pushing it. But what happened was, so now here's me no longer pushing it again. It's supposed to be me with my hands on my hips, if you're wondering what that is. Like, hey, I'm not pushing it, all right? And so now here's our velocity vector. Oh, I guess I could have put a velocity vector up here. Okay. So here's my velocity vector. But now, because I'm not touching it at all and we're assuming no friction, that means my net force is 0 and my acceleration is 0. So my velocity is going to be constant, but notice it's not 0. Okay. I used to have a video here, instead of a person pushing a cart, it was a video of a toddler pushing a bowling ball. And so I ended up not using that because it's rolling instead of sliding, whatever, you don't care. But you can all picture that, right? Like after you throw a bowling ball, it just keeps going and going and going and going, right? Because the lane is pretty flat, there's essentially no friction or air resistance or anything slowing it down. And so the bowling ball has a net force of 0. As a result, it doesn't accelerate and it just keeps rolling at a constant velocity. That's what I was trying to go for here, okay? Again, the wheels on the cart kind of simulate it being sliding on a frictionless surface, and it's not perfect. All right, now, in the real world, this is not true, because in the real world, we'd have a little bit of force of friction working against this velocity, and so it would slow down and eventually stop, right? If we let it roll far enough. All right, but again, oops, gross, sorry. We are assuming no friction, so. All right, so then what happens is, then the cart hit the table, right? So here's the cart moving along, boom, force of table, right? You could, if you wanted to, I guess, call that a normal force, right? But so that normal force from the table hitting it caused it to very quickly slow down and stop, right? What I probably should have done is, right? Because it's a really big force, so I should use a big arrow, right? And so now my net force is not 0, which means my acceleration is not 0. And so now my velocity decreased because it was moving this way. My net force was to the left, so that means my acceleration is going to be to the left, causing that velocity to decrease. Okay? All right, so that's the deal there. when I see you in class, I'll show you guys a couple demos. So here are the couple demos that I need to show you. Let's see if it'll let me insert a page. Oh, I don't know how to do this. All right, so here are the demos I need to show you in the next couple days. Tablecloth. And then your first homework assignment talks about driving into a brick wall and getting rear-ended in your car. All right, so those are the examples we'll do when I see you in class. Hopefully, before I get you started on the homework assignment. Okay? All right. Ooh, fan cart. That's the other one I got to show you. All right. Sometimes I forget what I need to do, so maybe remind me. I'm getting old. All right, there you go.